It should be an easy chapter. There's a few definitions, like 5 or 6 definitions, and then the same type of question over and over and over again. Okay, so we're going to do the theory, and then we're going to do a few experiments in front here. All right, so this chapter here is called chemical change, and we're going to look at the energy and the changes with the energy. Now, the first definition, you have done this here, is the dissociation energy. And the definition for dissociation energy is the energy required to break bonds. So another word for required is? Needed. The energy needed to break bonds. The energy required to break bonds. And the bonds that we speak about here is covalent bonds or ionic bonds. Ionic or metallic bonds. Okay, so those are the bonds that we speak of or speak about here. And if you want to break those bonds, you need energy. You require energy to break the bonds. And I'll go also busy with a new chapter, grade 12 chapter. Okay. Energy required to break bonds. I think that's what I wanted to say there. Then the next definition is bonding energy. That is the energy that is liberated when bonds are formed. What does the word liberated mean? Given off. Given off. The energy that is given off, or the energy that is liberated when bonds formed. So the same thing here, covalent, ionic, and metallic. So when you want to break a bond, so if you think here, if I want to break these two things apart, I need energy to break it. And when it forms, it releases energy. It gives off energy because it becomes more stable. It becomes more relaxed. Okay, now, here the table below, you've seen before. I don't think we used it. This table you do not need to know off by heart. I will either give you the table and you must use the information in it, or I'll just give you the values that you need from it. Now, in this table, you have 3 columns that repeat itself. The first column is the type of bond, so you can see the shape of the bond. Then you have the bonding length, so how long the bond is. And then you have the bonding energy. Now the bonding energy is the energy that is given off when a bond forms, but it's the same value as the dissociation energy. So it's the same thing. The energy that is required is the same as the energy that is given off or liberated. Okay, now if we just compare 2 bonds here, just to look at it, you compare the carbon single bond with the carbon double bond. You can see that the bond length decreases. When there's a double bond, they come closer together, and that makes sense. There's 2 things keeping them together instead of 1 thing. Okay, so they are closer together, but you can see the energy becomes more, because here you only have to break 1 bond, and here you have to break 2 bonds. So the energy is more. Okay, right, so this is what we have here. Now let's see how we use it. They calculate the net energy required or liberated in the following reaction. Now, when you're going to do an equation like this, you're first going to rewrite the equation in its Cooper notation. The Cooper notation is where you just draw the lines that represent the bonds. You don't draw the Lewis structure where you show all the electrons. Cooper notation is you just show the bonds. Okay, so there you have methane, and that's going to react with chlorine. And it gives you CH3, Cl, and HCl. Okay, so this is the reaction that was given there at the top, but just in Cooper notation, just to show the shape and the bonds. Okay, so you're going to ask yourself, what changed from the left-hand side to the right-hand side? What bonds broke and what bonds formed? Now you can see here, if we look at methane, and I look at the thing that looks the same, there's one thing that is different. Here you have a carbon-hydrogen bond, here you have a carbon-chlorine bond. So this bond needed to break so that this bond could have formed. Okay, so I'm going to highlight that for myself. I'm going to say, all right, it changed, it went from that bond to that bond. that changed. And if I look at the second one, I can see it went from chlorine to hydrogen chloride. Oh, sorry, there should be a line in between. Anyway. Okay, right. So we want to calculate the net energy. So we first have to calculate the energy that is needed to break bonds. And then we need to calculate the energy that was given off when bonds form. Lapello. What do we call it again when the energy that is needed to break bonds? The dissociation energy. So on the left hand side we have the dissociation energy, and on the right hand side we have the what energy, Tipiso? The bonding energy. Alright. So on the left hand side we have 1 mole of carbon hydrogen. Okay, so why do I say mole? Because there's only one bond. If we broke all 4 these bonds, then it would have been 4 mole. Or if this equation was balanced and there was let's say there was a 2 in front there. And so there's a 2 in front there. Then it would have been 2 times this, so it would have been 2 mole. So it depends how many bonds you break. It's 1 mole, 2 mole, whatever. Okay, and then the other bond that we needed to break was 1 mole of chlorine. Okay, so Kananela, I want you to please go find in the table the energy to break a carbon-hydrogen bond, and Panele for chlorine. 2,4,3. I believe you. I just want to check. For chlorine is 243. Is it plus 243 or minus 243? Plus, because you need the energy, you require the energy. Cananello for carbon, hydrogen. Four, 1, 4. Okay, so if we add that together, we get 657 kilojoule. That is how much energy is needed to break those 2 bonds. Okay, if we look on the right hand side, we have 1 mole of carbon chlorine that forms and 1 mole of hydrogen chloride that forms. Okay, so Tapelo, the first one, Unati, the second one.
The second one is 431.
431. And is it plus or a minus? Say again? No, it's a minus because the bonding energy is the energy that is given off. It's the energy that is given away. So we subtract it. Tapelo? Say again? 339. And it's also a negative. It's also the energy that is given off. Okay, so that gives you minus 770. Okay, so now we know the energy that is needed to break the bonds and the energy that is given off when bonds form. Now we want the net energy. Net energy is when you add the 2 together. So the net energy is when you say 657 minus 770 and you get minus 113, I think. Okay. So Miles, what does that mean if we get a negative net answer for you? Yes, it means more energy given off. So that means the environment is heated, heat given off. So the environment becomes warm, it becomes hot. Or another word to say that, we say it's an exothermic reaction. Exothermic reaction. Have you heard about the word exothermic? Okay. Going. Gone. Now a page of theory, and then we're going to look at certain examples. We have something called the heat of the reaction, and that's what you just calculated. The heat of the reaction is the same as the net energy. Okay, it has another name. It's also called an enthalpy. Enthalpy, or the heat of the reaction. And it is triangle H is the symbol. Now, Boitemilu, what does the triangle stand for again? If you see triangle, anything, what do you think of? Delta, what does that mean?
Something about heat.
No one knows what that means. Boitemilu, if you had to calculate a triangle, what did you calculate this year? Yeah, but even that, we didn't do so much. We did more last year. The triangle is final minus initial. The end minus the beginning. When you had to calculate the acceleration, it was final velocity minus initial velocity over time. You remember that from last year? Okay, so triangle is always final minus initial. So if we calculate the enthalpy, it is the product's energy minus the reagent's energy. It's the final energy minus the beginning energy. And the definition for that, it is the energy that is absorbed or released in a chemical reaction. Okay. So what is it basically? It's just a difference in the energy of the products and the reagents. Do we have more energy or do we give more off? Then the next definition there is the activation energy. The symbol for that is EA. The definition is the minimum energy needed for a reaction to take place. Okay, now I have used this example before, but it still works. Let's say you wake me up in the morning. Can you wake me up with a glass of water? No, I will not wake up. Not in my face, just to drink. Okay, don't wake me up with water in my face. Then can you wake me up with lemon juice? No. Tea? No. It must be coffee, and specific coffee. Otherwise, I will not get up out of bed. That is my minimum requirement to get out of bed. But some people, they say, Lapelo, you can give her a glass of water and she's up and she's chirpy and she's ready. Okay? My magis. Tumela. They just take notes. Welcome. Alright. So, the activation energy will differ for each reaction. Okay. Some will need lots of energy, some will require very little energy. So the activation energy is the minimum energy needed for a reaction to take place, for a reaction to start, for a reaction to happen. Now, that sounds more or less the same as what type of energy that we just discussed on the previous page. Tepang. On the previous page, we also discussed the energy. Yes? Yes. This is the same as the dissociation energy. The energy needed to break the bonds, or the minimum energy required for a reaction to take place. Then, before I go to the next definition, I first want to look here. Let's say we consider this reaction a hypothetical reaction is a made-up reaction. Hypothetical reaction where you say let's say we have A plus BC. Then we know that it's going to break up, right? Before it can bond again, it must first break up. Now, when it breaks up, we have, let's say this becomes positive. So we have, oh no, that will be, it doesn't matter. Positive, positive, and negative. Okay, so it breaks up into the ions before it can bond again. Okay, so that moment where it's all broken apart, but it hasn't bonded again, that we call, that part we call the activated complex. The activated complex. Okay, so what is the activated complex? The definition there is the unstable transition state from reactants to products. So it is unstable because it is not bonded, and therefore it has a high potential energy. It's unstable because it's not bonded, and therefore it has a high potential energy. Okay, so let's go just through this again. We start here, then these bonds need to break. So we need energy that breaks those bonds, and that energy is called the dissociation energy. So there we have the dissociation energy, the energy that is needed to break the bonds. It's also called the activation energy. Then we have the activated complex, all the ions that is broken up, and then they mix and they form again to form the product. So then they give off energy. That energy that is given off is called the bonding energy. Right, then the last bit of theory there is a catalyst. Now in school we speak about a positive catalyst because we do get something like a negative catalyst. Okay, but in school we only deal with a positive catalyst. What is a catalyst? The definition there is a substance that increases the rate of a chemical reaction. If you hear the word rate, what must you think of again? Divide by time. So it makes the time smaller. It increases the rate of a reaction without itself undergoing permanent change. Without, another way of saying that is without taking part in reaction. Okay, so you can either say without itself undergoing permanent change or without itself taking part in the reaction. Okay, now how does it increase the rate of the reaction? It does that by lowers the activation energy needed for a reaction. Okay, so ma'am, what does that mean? Let's say let's say there's a person, someone in Paris, and their soulmate lives in Johannesburg. Okay, what's the chances of them meeting? Very, very small. Because in Paris there's a lot of people, and in Joburg there's 1 million people. So the chances of them ever meeting is quite small. Okay, so they will search their whole life for that one person that they will meet. So maybe when they're 50, they will meet. Okay, but now clever people brought in things like Tinder. Okay, so what does Tinder do? It allows you to advertise yourself and other people themselves, and with your likes and dislikes and interests and whatever, and you can find someone, you can link with someone that has the same interests, and you swipe and you meet. So that makes it a lot easier for this person in Paris and the person in Joburg, that soulmate, to meet each other. Alright, so what did Tinder do? Did Tinder take part in the relationship? No, hopefully when you meet that person you delete Tinder. and you don't go on it again. So you don't do your relationship on Tinder. You get each other's cell phone number and you chat off Tinder. So Tinder didn't take part in the reaction. It just speed up the reaction. Okay. So that is a catalyst. It speeds up the reaction without taking part in the reaction. And how does it speed it up? It makes the energy needed less. Instead of searching for years and years and years and you have to meet every person and blah, 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 blah. Now the energy is much less. You just go on your cell phone. Okay, right. So that is what a catalyst does. What is wrong, Panele? Did you meet someone? Did someone else meet someone? Does someone else have a soulmate in Joburg? Okay. You know? No. Yo, this is just my personal opinion. Doesn't have to be yours. But there's nothing like a soulmate in life, ne? You work hard at a relationship. You just meet someone that you think, I can deal with this person's nonsense. Yep. Anyway, so that's just an example to get you to the idea. Right, so we get two types of catalysts. We get something like a homogeneous catalyst and a heterogeneous catalyst. Now, Katlego, what does the word homo mean? It means the same. Okay, so a heterogeneous means, obviously, it doesn't have to be opposite. It can be opposite, but it can also just mean different. Okay, right. So a homogeneous catalyst is where the catalyst is in the same phase as the reagent. So the catalyst is in the same phase as the reagents. Lepelo, phase, what do I mean by phase? Phase. This is an easy word, but I know learners, just forget it. Phase is solid, liquid, or gas. That is phase. In what phase will you find water at room temperature? Okay, right. So it means it's the same phase. If you work with a powder, it is also a powder. If you work with a blah, 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 blah. Now, the example that we're going to do today is this example here, where you have potassium chlorate. And if you heat that up, then it's supposed to decompose, to break apart, to give you potassium chloride and oxygen gas. But we're going to do this reaction and we're going to see that doesn't happen. Okay, we need to heat it up a lot and we can't heat it up to that high temperature. So we need to add a catalyst. And the catalyst we add is manganese dioxide. Okay, solid, that is a black powder that we're going to add. Say again? You can also use it. Yes, I think it's also used in the gun. Now that you mention it. I don't know. Alright, then we're going to get potassium chloride and oxygen gas. How do we test for oxygen? How do you test for oxygen gas? You're looking at Sipiso because you don't know. Sipiso, how do you taste for oxygen? A glowing splinter. I'll say. What we're going to do is we're going to put a glowing splint in test tube. And then if it ignites, what does the word ignite mean? It sets a light, it forms a fire. If it ignites spontaneously, woo, what does that word mean? If it ignites spontaneously, means by itself, then there's oxygen present. Okay, so I'll show you in a moment, but you need to know how do we test for oxygen gas. Tapelo, where did you guys go? Oh, really? Lucky, lucky. Okay, going. Gone. Right. So that is an example of a homogeneous catalyst because this is in the solid phase and this is in a solid phase. Same phase, homogeneous catalyst. Example of a heterogeneous catalyst is when you have an exhaust. Okay. Tapelo, your car, does it have an exhaust? Or did you take it off? It's there. It's good. Okay, because your car gives off very poisonous, dangerous gases like nitrogen monoxide and carbon monoxide. They are poisonous gases. They are bad gases. Okay. Beta gases, still not the best, but beta gases is nitrogen dioxide and carbon dioxide.
Is that what they use in hybrid cars?
In?
Hybrid cars.
Hybrid cars gives off water. Ne? Yeah, it works with water and electricity.
How?
Let's not go into that just now. Are you the new Chiamo? Alright, so to go from the one to the other one, you need very, very high temperatures. Okay, like, I don't know the exact temperatures, but let's say you need about 1,000 degrees Celsius. Okay, and obviously to create that in your exhaust is extremely difficult. So what they do is they make your exhaust of platinum. And a platinum acts as a catalyst, so it lowers the energy. Now you only need, say, 100 degrees Celsius. If you touch the exhaust, do you burn? Yes, it's hot. Don't go try it at home. Okay, so in your exhaust there's oxygen present, and then with the help of platinum, that now you only need to heat it up to 100 degrees Celsius, you can convert it into beta gases. Okay, so this platinum is an example of a heterogeneous catalyst. Why? Because platinum is a solid, your exhaust is a solid, and these are gases. So they're different phases. So there at the top, I said a heterogeneous catalyst is where the catalyst is in a solid state and the reagent is in a liquid or a gas phase. The reagents are the thing on the left-hand side, gases, and platinum is a solid. So there are different phases. Okay, so that's the two types of catalysts that we do get. Now we're going to look at the two different types of reactions that we find. Okay, the first type of reaction is called an exothermic reaction. An exothermic reaction, so the definition for that is when there's a release in energy. A release in energy. Okay, so that means if there's a release in energy, that the bonding energy is greater than the dissociation energy. Meaning, more energy given off than required, than needed. So that means the heat of the reaction or the enthalpy is negative. So a way they can show you, indicate to you that the reaction is an exothermic reaction is they'll say the heat of the reaction is negative, or the energy that is given off the products is bigger than the reagents. Okay, right. So let's look at this hypothetical reaction. Now, this graph you need to know very, very, very well. You need to know everything on this graph. And you need to be able to draw a graph like this. Okay, so in this graph we have on the y-axis, we have our potential energy. And on the x-axis you have time, or reaction coordinate is what they call it, but that's basically the time. Okay, you can see here we start with the energy of the reagents. Then to break these bonds we need energy. We need activation energy or dissociation energy to break the bond, so we need it. So it goes up the energy. Then we have our activated complex, there where all the bonds are broken and we just have the different pieces. And then it gives off energy when bonds form. When bonds form, they become happy, they become stable, so it gives off energy again. And here you can see it gives off more energy than the energy that is needed. So it gives more off more energy, so it's an exothermic reaction. Okay, so we're going to highlight here the different things. We're going to highlight, first of all, the activation energy, EA. The activation energy, or another name for that, is the dissociation energy. Alright. Then you have the unstable activated complex. That is very unstable. It has a high potential energy. Alright, and then it gives off energy there. That energy that it gives off is called the bonding energy that it gives off. When bonds form, it gives off energy. And now the difference between the energy of the reagents and the energy of the products, that difference there is called the heat of the reaction. The net energy. This is the same as the net energy. Okay. So let's say this E1 was 50, this one was 200, and let's make this one 400. So I made these values up now. 50, 200, 400. Then if we want to calculate the heat of the reaction, then it is the final minus the initial. Okay, so it will be 50 minus 200. The final energy, 50, minus the initial energy, 200. So it will be 50 minus 200, oopsie, and that gives you minus 150. So you can see there, if the enthalpy, or if the heat of the reaction is a negative, if it is smaller than 0, then it is an exothermic reaction. Okay? Or when you look at this graph and you see this line ends lower than this line, then it's an exothermic reaction. Now, with reactions, time is money. We want to save time. We want to save money. So we want to add a catalyst. Okay, now a catalyst does two things. A catalyst makes it complete the reaction faster, and it lowers the activation energy. That's the two things that a catalyst does. So if you look here, there's where we add a catalyst. It did two things. Okay, you can see it made it complete it faster, so the line ends quicker. So it ends quicker this time. And it lowers the activation energy. There you can see it doesn't have to go up all the way to there. It can only go up till there. Okay, so that is what a catalyst does. So what they sometimes ask in the exam is they give you this graph, the original graph, and then they'll ask you to redraw this graph and now add a catalyst. Show how a catalyst will change it. So then you'll show it is lower here and it completes faster. Okay, right. Now how do we write this down in a reaction? You can write it down in one of three ways. The first way is after the reaction, after you've written down the reaction like this, Then you write a comma. And then you say the enthalpy is negative. Or you say the enthalpy is lower than 0. Smaller than 0. Or, if it's an exothermic reaction, then it gives off energy. So then you can write the energy as one of the products. You say, okay, here we have carbon reacts with oxygen, gives you carbon dioxide, and it gives you energy. So there you write it as one of the products. Here you write it as like a side note. This is a reaction. Oh, and by the way, the enthalpy is negative. Okay. Then there, I give you another example where we have the side note where you say, right, comma, whatever that's negative. Or you say it gives off energy as part of the products. So you see it gives off energy as part of the products. Can you see that in the first example, the two values are the same size? And in the second example, they are different sizes. Why?
Then the other one, it's going to give 2 HF.
Yes, in the second one, you can see the mole ratio is 1 to 2. It gives you 2 mole. And the energy is per mole. Remember here at the first page, we said 1 mole, 1 mole. Now it gives you 2 mole. So that was per mole, that is for 1 mole. Here it gives you 2 mole, so this is 2 moles times 268. Okay, right. Then we get something like a spontaneous and a non-spontaneous exothermic reaction. Now, a spontaneous, you know the word spontaneous? If someone tells you you're a spontaneous person, Kananelo, what do they say? You are not so spontaneous. I think the most spontaneous person in this class is a toss-up between Banele and Tapelo. Maybe Tapelo. Huh?
What's continuous?
What does the word spontaneous mean?
Yo, man, you just said it. These guys. You just said it.
Say again?
Nice.
Mm-mm.
When you beat yourself.
When you?
Beat yourself.
When you do it yourself? Yes. I would like a better explanation. When you don't need, so I won't have to say, okay, how would I ask this? Who would like to, I need someone to help me. And then some people would be like, no. And then some people would be like, me. And it just goes. So spontaneous is, it just happens by itself. It just goes by itself. It doesn't need extra energy. But other people need to say, will you please do this for me? Please, will you do, can you do this for me? And then later on they say yes. Okay, so I'm not saying that person is rude. I'm saying some people need more energy. They won't just go into a room and start chatting with other people. And some people will do that. Okay, so spontaneous in chemistry means there's no activation energy needed. You don't need to stir it or heat it or whatever. It just happens. It just goes. Okay, so there's 2 examples there. I want you to know the second example. The second example is where you take sodium hydroxide, sorry, and you dissolve it in water. Sodium hydroxide, and you dissolve it in water. Then it will just happen. The reaction will just take place. I'm going to show it to you in a moment. Okay? Now, this is an example of spontaneous. And how do we know it's exothermic spontaneous? This will heat up. It will become warm. So you will actually feel it heats up. It becomes warm. Okay? Another example that I want you to add there is where let's say we take lithium and we let it react with water. Lithium, and you let it react with water. Then you'll get lithium hydroxide and hydrogen gas. Now I know this is not balanced. You'll need a 2 there, and a 2 there, and a 2 there. But it doesn't matter. That reaction will just happen. And I'm going to show you that one as well. It just takes place. You don't have to do anything to it. It just goes. Okay, so spontaneous. The non-spontaneous reaction needs activation energy. It needs a bit of help to get going. It doesn't just happen on its own. Okay? Like heating it up or like stirring it or something like that. So it just needs a fire. Okay? Now the example I want you to know is this last one here. Where you take magnesium ribbon, you find that it sparkles when you have a birthday at Spur, they give that sparkles. Alright? So when it doesn't just start to sparkle, but when you light it, it just goes. You don't have to keep the flame there. You just give it a bit of energy and it goes. Alright, so we heat that up there. It needs a bit of energy. Okay. Then we're going to go to endothermic reactions. Endothermic reactions. Now that's just the inverse of an exothermic reaction. Okay? That is where it absorbs energy or it cools the environment. It makes the environment cold. I want to check that I say everything. Okay? So here we can say that the dissociation energy is greater than the bonding energy. Here you need more energy. You need more energy. Okay, so here the enthalpy is greater than 0. Okay, so if we look at this example, you can see it's literally just the mirror image, of exothermic. So here you can see again potential energy versus time. Here we go up. So we need a lot of energy, we require a lot of energy, and very little energy is given off. So when you see that it ends higher than where it started, then it's an endothermic reaction because it needs more energy than what is given off. Okay, so what is important here, obviously, is your activation energy or your dissociation energy. Then we have our activated complex there at the top. Then we have our bonding energy, the energy that is given off, the bonding energy. The energy that is given off when a bond forms. And then we have the difference between the energy of the reagents and the energy of the products. That difference there is called the heat of the reaction. The heat of the reaction. So let's say the first one there is again 50, 200, 400. Then if we were to calculate the heat of the reaction, it's always final minus initial. So it would have been final is 200 minus 50, and that gives you 150. Remember, it's final minus initial. Okay, then again you see we have the catalyst there, and what does a catalyst do? It makes it complete it faster and it lowers the activation energy. All right, where are we for questions? Panele. What did you answer, Cananelo?
No, you answered for me spontaneous.
Well, but let's ask you again. Cananelo, for the, now listen carefully, for the reverse reaction, what is the activation energy?
Can you give me true name?
Reverse reaction is from the end to the beginning. So some reactions are reversible, like you can melt water and then you can freeze it again, melt it and freeze it, melt it. So there's reversible reactions. So for the reverse reaction, what is the activation energy?
Is it a number?
It is a number. Number for this one. So this is the forward reaction. What for the reverse reaction? For the reverse reaction, what is the activation energy?
Negative 400.
Number it are.
Say again.
Negative 40.
Now that is the enthalpy or the heat of the reaction for the reverse reaction. So here we calculated the heat of the reaction for the forward reaction. Now I'm just asking for the reverse reaction, what is the activation energy? What is activation energy? From start to activated complex. What is the energy for the reverse reaction? What is the energy to activate it, to start the reaction? So from the start to the activated complex. What is that? 200. You start at 200, you end at 400. What's the difference? 200. Questions like that you need to know. That's why I ask it now. Okay, let's see how do we write this down. Okay, again the same as the previous one. You make a comma and then you write it. Or now you write it as one of the products. You need the energy. You require the energy. So here it is one of the, not the products, sorry, the reagents. Because you require the energy. Okay. Then here we also have spontaneous and non-spontaneous reactions. So now you must wonder, ma'am, how do we get an endothermic reaction that is spontaneous? Because endothermic, it needs energy, So how is it spontaneous? Spontaneous here means it absorbs energy from the surroundings. So you don't need to add extra. You don't need to heat it up or stir it or whatever. It just takes energy from its surrounding. Okay? And the example I want you to know is this one here. Okay. You just need to know at this point of time that when we dissolve salts in water, that is an endothermic reaction, that is spontaneous. Think about it. If you take salt and you put it in water, does it dissolve? It goes down, but not all of it goes down. Some of it dissolves on its own. Okay, why does that happen? Because it takes energy, it takes the temperature from the water. So actually, if you put your thermometer in, you'll feel that it actually gets cooler, your water, when you add salt to it. Okay, now, how do we know it's an endothermic? So that is spontaneous. How do we know it's endothermic? When will water dissolve faster? When you heat up the water or when it's cold? When it's hot. So that is your clue that it's endothermic reaction. It takes energy. If you make the environment hot, then it takes the energy from the environment. Okay, right. Then a non-spontaneous endothermic reaction is where you need to heat it continuously the whole time. You can't stop. You must heat it and heat it and heat it and heat it. You can't stop it. Okay? And the one I need you to know is the second one that we're going to do as well. Okay, we discussed it already where you have potassium chlorate and you need to heat it up the whole time. Otherwise, it will not take place. It will not decompose. All right, so I'm going to stop the video now and then we're going to do the practicals. Okay, your homework, yes, I am that person that gives homework, is page 5, 6, and 7. Okay. Right, now 5, 6, and 7, 5 will take a bit longer, but 6 and 7 is short answers. Like I asked, say whether it is endo or exothermic. And then you must just write the words endo, exo. The next question is you must give me some values. Okay, right.